Welcome back to Differential Equations. In this lecture, we're going to learn how to solve non-homogeneous ODEs with a method called undetermined coefficients. All right, in the previous lecture, we introduced this type of differential equation we'll be solving, what we call a second order linear ODE with constant coefficients. All right, in that lecture, we introduced the two types that we'll be learning how to solve. The first type was what we were calling a homogeneous ODE. Homogeneous in the setting of second order differential equations just means the right-hand side is zero. All right, so this was the, topic of our previous lecture. We covered that in detail. When the differential equation equals zero, we get our characteristic equation. We solve that for the characteristic roots, the values of R. And there are three possibilities for the values of R. You could have distinct real roots, a single repeated real root, and also distinct complex roots. All right, so we covered this in detail. Before you try to understand this lecture, make sure you are extremely comfortable with everything related to homogeneous ODEs, the characteristic equation, and the three different possibilities for solutions and values for R. All right, before we move on to the second type, a non-homogeneous ODE, let's introduce a new term, something that we're going to call the complementary solution, which will denote it by Y sub C. Sometimes I'll just call that YC just to make it easier to pronounce. All right, and what the complementary solution is, it is the general solution from before. Since the right-hand side of our differential equation was zero, we look for the solutions Y1 and Y2 that solve that. Those were linearly independent solutions. And now we put them together and give them a different name. We're not calling it the general solution now, but the complementary solution. That term will make sense in a few minutes. All right, so let's just be clear. The complementary solution, YC, which is C1 times Y1 plus C2 times Y2, where C1 and C2 are your constants, this is a solution to the homogeneous ODE where the right-hand side equals zero. All right, so if you were to take YC and plug that into the differential equation, the function y and its derivatives combine to give zero, since that is a solution to this ODE. All right, so keep that in mind when you plug YC, the complementary solution, into the homogeneous ODE, y and its derivatives combine to give zero. All right, the topic for this lecture is non-homogeneous ODEs, where the right-hand side is not zero, so it could be any function of x. All right, and what I want to point out is that the complementary solution is not a solution to this non-homogeneous ODE. And the reason for that is when you take the complementary solution, YC, which is a linear combination of Y1 and Y2, when you plug that in to the differential equation, y and its derivatives will simplify to zero if you plug in the complementary solution. For our purposes, we need a function such that when we plug it into the differential equation, y and its derivatives simplify to the new right-hand side, g of x, which is not zero. All right, so the complementary solution gives y and its derivatives combining to zero, which is not what we want here. We need y and its derivatives to combine to g of x. So what this means is the complementary solution is not a solution to the non-homogeneous ODE. we need to find a function y such that y and its derivative simplify to g of x. All right, and that's going to be what we call the particular solution, which we'll write it as y sub p, and I'll call this yp when we're talking. All right, now what we're going to call our general solution, this is a combination of the complementary solution, which solves the differential equation where the right-hand side equals 0, and the particular solution, which is your solution to where the right-hand side is g of x. Now, since our differential equation is linear, remember, linear ODEs, a linear combination of solutions is another solution. So once we find the complementary solution, and once we find the particular solution, we add them together to give us the general solution. All right, I realize that was probably a mouthful, just to understand all the terms and hard to keep track of things without concrete examples. So let's take a look at one here. We're going to go through this just to kind of outline the basis for undetermined coefficients, and then eventually we'll come back to solving this. All right, so it should be very quick for us to find the complementary solution. All right, so that's pretty much our previous lecture. We're generally going to split these into two parts. So first, we're going to solve the homogeneous ODE, where the right-hand side equals 0. All right, and we can find that no problem. You get your characteristic equation, and you get distinct real roots for r, -1 and 2. And that gives you your y1 and y2, e to the negative x, and e to the 2x. So the complementary solution, yc, is c1 e to the negative x plus c2 times e to the 2x. All right, what we're interested in is how do we find a function such that y and its derivatives differentiate not to 0, like with the complementary solution, but we're looking for a function such that y and its derivatives combine to 4x squared. So we know what the complementary solution is, but what is the particular solution? Well, let's point out some ideas that you already know, but we're going to take a big picture point of view. So we're going to, instead of looking at this at a very fine scale, we're going to kind of take the 10,000 foot point of view. So from really high up. All right, and let's just step away from differential equations, and let's take a look at these 3 examples going all the way back to Calculus 1. All right, the derivatives here are not meant to be challenging, but what I want you to notice is an interesting pattern with certain types of functions. Notice if we were to generalize each example there of those 3 derivatives, the first one we can say generalizes to the derivative of a polynomial is another polynomial. The second example generalizes to the derivative of an exponential function is another exponential function. And the last example there, the third one, in terms of sine and cosine, when you differentiate sine or cosine, you get sine or cosine back. All right, and what I want to point out here is we're being very careful to not say trig functions in general. There's something very special about sine and cosine with respect to second order derivatives. They come back. So think of sine and cosine individually. When you differentiate them twice, you get back to where you started. So unlike e to the x, which just comes back after the first derivative, sine and cosine basically take 2 derivatives to get back to what you started with. All right, why we're not saying the derivative of a trig function is another trig function is something goes wrong with the other 4 trig functions besides sine and cosine. Sine and cosine are special because after 2 derivatives, the function comes back. Let's just take a look at the derivative of tangent, which is secant squared of x. No matter how many times you differentiate tangent, you will never get a tangent coming back. The first derivative of tangent gives secant squared. Then you have to differentiate secant squared using the chain rule. And that leads to using the product rule, and you don't get tangent back after any finite number of derivatives. Same goes with the derivative of secant, which is secant times tangent. Differentiate secant multiple times, it just keeps getting more complicated. You'll never get it coming back to the function that you started with. All right, so what's important about polynomials, exponentials, and sine and cosine functions? Well, they are functions that differentiate to the same type of function. Polynomials differentiate to polynomials, exponentials differentiate to exponentials, and sine and cosine differentiate to sine and cosine. And again, keep in mind here, because we're learning about second order differential equations, we want to think about things differentiating back to themselves up to 2 orders of derivatives. All right, so how does this help us here with looking for a particular solution? For this example at the top there, how do we find a function y such that y and its derivatives combine to give 4x squared? What type of function is 4x squared? I think it's a polynomial, right? And what types of functions differentiate to polynomials? Another polynomial. So the basis for undetermined coefficients relies on being comfortable with these 3 types of functions that differentiate to themselves. In short, how the method of undetermined coefficients works is we make a guess for the particular solution, yp, based on the form of g of x, that is the non-zero right-hand side of your differential equation. And in that guess for yp, there's going to be unknown or undetermined coefficients. It's very much like partial fraction decomposition from Calc 2, where you write down your partial fractions in terms of constants, a, b, c, d, however many that you need, and then you try to solve for those values of the constants. We're basically doing the same thing here, but with a choice for the particular solution. All right, so for this example, just to kind of summarize how this works before we go into detail for how we choose the particular solution, let's just take a look at the right-hand side of the differential equation, what we're going to call g of x. Here, it's 4x squared, and let's just try to think, what type of function is that? For this lecture, we have really 3 types to keep in mind: polynomials, exponentials, sine and cosines. All right, and the right-hand side, 4x squared, that is a degree 2 polynomial. Now, what type of function will differentiate and combine with y and its derivatives there in your differential equation to a degree 2 polynomial? Well, another degree 2 polynomial. So for this example, we would try a general degree 2 polynomial, something of the form ax squared plus bx plus c. And keep in mind here, this particular solution is combined with yp and its first and second derivatives according to your differential equation. So depending on the signs, positive or negatives, we want to find terms that essentially cancel out and leave you with 4x squared, the right-hand side for this example. All right, hopefully this makes sense. Basically, we look at the right-hand side, g of x, and we use the form of g of x to make a guess for the particular solution. Our guess contains unknown coefficients. Here we need 3 of them, A, B, and C. Some examples we might need more, which we're going to see in example 1. So when you're ready, let's get to our first example, not on solving differential equations, but just making sure for a given differential equation that you can choose the right form for the particular solution. All right, before we move on, I want to point out this important kind of feature for undetermined coefficients. It's a simple, straightforward method, but there's a big drawback. Undetermined coefficients is only going to work when g of x, the right-hand side, is a combination of polynomials, exponentials, and sine and cosine. What that would mean is any type of function that's not in that list, for instance, if maybe your right-hand side were tangent of x, so if g of x equals tangent of x, undetermined coefficients will not work. So this method is simple and straightforward, but the drawback is it doesn't always work. The following lecture, variation of parameters, will have a more general method, but there's still some complications with that. All right, when you're ready, let's get to example 1. All right, and this, we're not going to be solving differential equations yet, but we're going to make sure that we're comfortable choosing the right form for the particular solution based off of the form of g of x, our non-zero right-hand side. All right. Now, instead of writing down a full differential equation, we're just going to focus for each equation here, the right-hand side changing to these listed g of x's there. Now, towards the end of this lecture, we will point out what you need to be aware of and what you need to be careful with when choosing your particular solution, but we're not there yet. So for these examples, we're just going to focus on g of x and how that would influence our choice for the particular solution yp. Our last example, we'll get to the trickier examples that might require us to kind of go against what we'll see here in this example. All right, so maybe you feel comfortable trying this. We're going to look at the form of g of x and then basically identify it and generalize it to a general form for yp. So maybe give an attempt at part A, pause if needed, and give yourself a few seconds to write down the corresponding particular solution. All right, this is very similar to our intro example. For part A, g of x is x squared plus 1, a degree 2 polynomial. So like the first example, we just try a general degree 2 polynomial, ax squared plus bx plus c. All right. For part B, where g of x is 2x cubed minus x plus 3, that is a degree 3 polynomial. We try a general degree 3 polynomial. You can probably see the pattern here. If g of x is 2x to the 4th, a degree 4 polynomial, just try for yp a general degree 4 polynomial. So you can see in these 3 examples, as the degree of your polynomial increases, you introduce more coefficients. All right, for part D, g of x is 3 times e to the 2x, which is an exponential function. So we try a general exponential function with a constant a out front, but the exponent is still 2x. Why? Think about using the chain rule to differentiate e to the 2x. You get a factor of 2 coming down front due to the chain rule, but the exponent, 2x, that stays the same. All right, let's take a look at a fifth example here. All right, g of x is sine of 3x. And due to how second derivatives work for sine and cosines, the first derivative, it switches, but then the second derivative, it comes back. If our g of x contains a sine term, sine of 3x, our particular solution might need to include a cosine of 3x term. So here we would try a particular solution of the form a times sine of 3x plus b times cosine of 3x. And again, the reason for that, this particular solution would be combined with its first and second derivatives. So there could be some cancellation of terms with various signs having your need for a cosine of 3x term in there. All right, let's take a look at one that's a little more complicated. Part F, where g of x is x times cosine of x. Now, this one is a degree 1 polynomial, x, and then we're multiplying it by a sine or cosine function. So what we keep in mind is when we have a single sine or cosine, we need to include the other one as well. And since we are multiplying cosine by a degree 1 polynomial, our sine and cosine terms should be multiplied by general degree 1 polynomials. So here, our particular solution that we would try is ax plus b times cosine of x plus cx plus d times sine of x. All right, part G is very similar. We're starting to combine some of the various ideas here for choosing the form of yp. And here, for example, g of x is a degree 2 polynomial times an exponential function. So our choice for yp would be a general degree 2 polynomial times e to the negative x. All right, let's take a look at one last one where g of x is 3x squared times cosine of 2x. This non-zero right-hand side is a degree 2 polynomial times sine or cosine. So we include cosine of 2x as well as sine of 2x in our particular solution. But each of them is multiplied by a general degree 2 polynomial. So our choice here for this g of x, our choice for yp would be ax squared plus bx plus c times cosine of 2x plus dx squared plus ex plus f times sine of 2x. All right, from these examples, you can see, depending on the complexity of g of x, you could have a very small number of coefficients to solve for. Or here, in example H, we have 6 coefficients to solve for. All right, before we get to some examples, and again, the examples we'll be getting to are the straightforward ones, where we don't have to mention the things to be aware of for choosing yp yet. Again, we're going to save that for the last example in this lecture. Let's just give a brief overview of how we're going to solve non-homogeneous ODEs. All right, so pause if needed to copy these into your notes first. These steps would be good to refer to when you go through the examples like we will in a moment. All right, and our first step is we're going to find the complementary solution. This is solving the homogeneous ODE. We're going to make the right-hand side 0. So step 1, solve and find the complementary solution. And that was basically the previous lecture. All right, second step, once you have found your complementary solution, we now then try to find the particular solution. In these examples, we'll be using this method that we're learning about, undetermined coefficients. And once you find your particular solution, which includes a lot of algebra in solving for your coefficients, you then combine YC, the complementary solution, with YP, the particular solution. We add them together to give us what we call the general solution. If the differential equation has initial conditions, you can use the initial conditions with the general solution, YC plus YP. Make sure to do that at the end here once you have found your particular solution. All right, so again, pause if needed. And when you're ready, let's get to example 2, our first real example on solving a non-homogeneous ODE with this method, undetermined coefficients. All right, you maybe want to attempt this, but since this is our first actual example, we'll go through this together. But if you want, pause right now, make an attempt, give yourself maybe 5 minutes if you feel like you're understanding how undetermined coefficients works. If not, just pick up with this in a few seconds. We'll go through this one together. All right, so ideally, you're referring to your notes right now. I told you to copy them into your notes, didn't I? If you need to, pause, go back now, copy them to your notes, and then fast forward to now again, which I guess is the future. Time travel is complicated. Anyways, let's get to step 1, finding the complementary solution. All right, we make the right-hand side 0. We get our characteristic equation. This one easily factors. So we get our characteristic roots, -1 and 2, very quickly. And that leads us to the complementary solution, YC, which is C1 e to the -x plus C2 times e to the 2x. All right, that should not be difficult. That should go very quick. So we can move on to step 2, finding the particular solution. All right, here we first start by looking at g of x, which is 4x squared, which is a degree 2 polynomial. So we would try a particular solution of the form, a general degree 2 polynomial. So we'll use YP as ax squared plus bx plus c. All right, this would be a good time to pause to see if you can complete this. I feel confident that some of you, with your mathematical skills, can put the pieces together for how we're going to solve for the values of a, b, and c here. So if you're up for it, pause and give yourself maybe 2 to 3 minutes to see if you can solve for the values of a, b, and c. Remember, we want YP to be a solution to the non-homogeneous ODE, which means when we plug yp in, y and its derivatives, we want them to all combine to 4x squared. We'll check in 2 to 3 minutes. All right, welcome back. Let's go through some of the work. So with yp, for this to be a solution, we need yp and its first and second derivatives. All right, this is very straightforward. No special differentiation rules are needed. All right, and we're going to take this set of yp and its derivatives and then plug them into the ODE, the non-homogeneous ODE, since yp is the solution to the non-homogeneous ODE. All right, so just be careful. We're plugging in yp as well as its first and second derivatives. And the right-hand side is 4x squared. All right, so let's plug all those in. And you can probably see that there's 3 types of terms on the left side. You have your x squared terms, your x terms, and then your constant terms. So multiply, FOIL, expand this all out, and then collect your like terms on the left side. All right. Now, how we proceed from here is almost identical to a way that you would solve for your constants in a partial fraction decomposition from Calculus 2. From here, we're going to use a method called Equating Coefficients, and we're basically going to equate the coefficients of like terms on each side of this equation. Now, just so you can see how you would get 3 equations, and we need 3 equations because we have 3 unknowns, think of your right-hand side not as 4x squared, but think of it as 4x squared plus 0x plus 0. Now we can compare coefficients of x squared on each side. We can compare coefficients of x on each side. And then we can compare the constants or constant terms on each side. And doing that, we should get these following 3 equations. Comparing x squared terms, we get negative 2a equals 4. Comparing the x coefficients on each side, we get negative 2a minus 2b equals 0. The 0 is coming from there being no x term on the right-hand side, but we can think of that as being 0 times x. And then our third equation, comparing the constant terms on each side, is 2a minus b minus 2c equals 0. Now, at this point, we have turned it from a differential equations problem into purely an algebra problem. We have a system of equations, 3 equations for 3 unknowns. Have fun. Give yourself a minute. This one should solve very quickly. All right, welcome back. This system of equations is a good one to start with. It basically cascades from the first equation all the way down. Notice the first equation, you can easily solve it to get a as negative 2. Once you have a, you can plug that into the second equation to get b, which is 2, and then plug a and b both into the third equation, and you should get c as negative 3. So this one isn't as intimidating as it sounds. This system of 3 equations for 3 unknowns actually solves very quickly and easily. All right, and those three values that we found, the values for A, B, and C, that now tells us what our particular solution is. So we just plug them in back above to get that our particular solution, YP, is negative 2x squared plus 2x minus 3. We combine YP, we add that to YC to get our general solution, which we have here. All right, and that is a complete problem, start to finish, implementing the method of undetermined coefficients. In the second part, we'll get to a lot more complicated examples, ending with some of the exceptions we need to be aware of when choosing YP.